Welcome to today's presentation on Shockleys diode, a groundbreaking semiconductor device. Invented by William Shockley in 1947, the Shockley diode played a vital role in the development of modern electronics. This presentation aims to provide an overview of the diode's working principle, characteristics, construction, and application. The invention of Shockley's diode. William Shockley, along with John Bardeen and Walter Brattain, invented the point-contact transistor at Bell Labs in 1947. During their research on semiconductors, Shockley proposed the idea of a new diode called the Shockley diode. It was the first practical semiconductor diode capable of providing amplification, which laid the foundation for further advancements in electronic devices. The Shockley diode or PNPN diode is a four-layer, PNPN, two terminals, namely anode and cathode, semiconductor switching device. It is also called as four-layer diode. It functions like a normal diode without any trigger inputs. In reverse biased condition, no current flows through it, and in forward biased condition current flows through it when the voltage across it is more than the break-over voltage of it. The symbol of the Shockley diode resembles a conventional PN diode, but it is only half of the triangle. Construction of Shockley diode. It is made of four alternating layers of p-type and n-type semiconductor layers. They are sandwiched together to form a PNPN structure that resembles a thyristor. The combination of these four layers forms three PN junctions J1, J2, and J3. The anode terminal is connected to the outer P layer, while the cathode terminal is connected to the outer N layer. The structure of the Shockley diode can be understood using two-transistor analogy. The four layers PNPN can be split into two BJT transistors, T1-PNP and T2-NPN, connected with each other. The base and the collector of both BJTs are connected together, while the emitter of PNP is the anode and the emitter of NPN is the cathode. The junctions J1 and J3 are the base emitter junctions of PNP and NPN respectively, while junction J2 is the combined base collector junction of both transistors. Its structure can also be split into the PN junction diodes D1, D2, and D3 as shown in the figure. The diode D2 is in opposite direction to the diodes D1 and D3. The anode of D1 is Shockley anode while the cathode of D3 is Shockley cathode. Working principle of Shockley diode. The Shockley diode can be connected in forward bias and reverse bias. In forward bias, it conducts current if the applied voltage increase above break-over voltage, while in reverse bias it blocks current. Let's explain these mode of operation. In forward bias, the anode of the Shockley diode is connected to a higher potential than the cathode. As there are three junctions J1, J2, and J3, with the application of forward bias voltage, the junction J1 and J3 becomes forward biased, but the junction J2 becomes reverse biased. Due to this reverse biased junction J2, the Shockley diode does not conduct current and the applied voltage appears across the diode as if it's blocking the current flow. However, a very small leakage current flow through it is called forward leakage current, which is dependent on the temperature. This mode is called forward blocking mode. In forward blocking mode, the Shockley diode is in off state offering high impedance. Therefore, the diode acts as an open switch in this mode. Forward conduction mode. As the applied voltage is increased, the diode leakage current slowly increases. When the voltage reaches the avalanche breakdown voltage, called breakover voltage or breakdown voltage or forward peak voltage, the reverse biased junction J2 starts conduction. The resistance of the J2 junction decreases and behaves like a forward biased junction. The diode current rises up to a limit called holding current. The diode switch on and the voltage across the diode starts to decrease while the current increases. This mode is called forward conduction mode and the Shockley diode is in on state. Reverse blocking mode. In reverse bias, the anode of the Shockley diode is connected to a lower potential than its cathode, making the anode more negative to the cathode. The junction J1 and J3 are reverse biased while the junction J2 is forward biased. This mode is called reverse blocking mode. The diode is in an OFF state showing very high impedance. However, there is a very small leakage current called reverse leakage current. If the reverse voltage exceeds the avalanche breakdown voltage of J1 and J3, called the reverse breakdown voltage, the diode breakdown, and a very large current starts flowing through it. This should be avoided at any cost to maintain the reverse voltage below the reverse breakdown VBR limit because it permanently damages the diode. Shockley diode equation. The equation of the Shockley diode shows the relationship between the diode current and the applied voltage in both forward and reverse bias. Here is the Shockley diode equation, where ID is the diode current, IS is the reverse bias saturation current, VD is the applied voltage across the Shockley diode, N is the emission coefficient, typically between 1 and 2, determined based on the fabrication process. VT is the thermal voltage. VI characteristics of Shockley diode. This graph represents the relation between the voltage and current through the diode. The x-axis represents applied voltage, while y-axis represents the diode current. Reverse characteristics. Shockley diode does not conduct current in reverse bias. Initially, there is a small reverse leakage current that depends on the thermally generated minority carriers. Thus it varies with temperature. As the reverse voltage increases, the leakage current gradually increases until the voltage reaches the reverse breakdown voltage, avalanche breakdown occurs, and a large current starts flowing through the diode. The reverse voltage should be maintained below reverse breakdown voltage as it permanently damages the device. Forward characteristics. The forward characteristics show the behavior of the Shockley diode in forward bias. It is divided into 3 regions. Forward blocking region. Initially, the diode does not conduct until the voltage exceeds the breakover voltage VBO. However, there is a small leakage current called the forward leakage current. The applied voltage appears across the diode. The device is in cutoff or off state. Negative resistance region. When the voltage exceeds the breakover voltage VBO, the current starts to increase while the voltage across the diode decrease, showing negative resistance. Therefore, this region is known as the negative resistance region. The voltage decreases until the current reaches a limit called holding current IH. This voltage is called knee voltage VK. However, this state remains for a very short time and the diode quickly jumps into the next region. Saturation region. Once the diode current reaches the holding current IH, the voltage across the diode does not reduce further than knee voltage VK, whereas the current drastically increases, having low voltage across the diode just like a short circuit. This region is known as the saturation region and the diode is said to be in the on state. Applications of Shockley diodes. The Shockley diode is used for the following applications. Triggering SCR. Shockley diode is used for triggering an SCR using the following circuit. It controls the triggering of the SCR. When VDC is applied, the capacitor C charges through the resistor R. When the capacitor voltage reaches the breakover voltage of the Shockley diode, the diode starts conduction and triggers or switches on the SCR. Used as relaxation oscillator. A relaxation oscillator is a type of nonlinear oscillator that produces a non-sinusoidal periodic waveform. They are used for generating low-frequency signals to power blinking LEDs, beepers, function generators, etc.